Center of Mass and Applications with High Diving by Taylor Reinhardt. Center of mass is the point at which a system of masses can be treated as a point mass. This is very important because it simplifies any calculation for motion, rotation, velocity, and any of the forces acting upon the body. The center of mass is not necessarily on the body, however, but it is within the body's parameters. For example, in the figure shown to the right, the center of mass could not be below the figure's feet or above the figure's head. These each represent extremes for the center of mass.
The center of mass is calculated by computing the summation of each uniform density object, in this example, the arms, legs, torso, and other ligaments, center multiplied by the segment's total mass.
This is divided by the summation of the segment's mass, also known as the total mass of the body or the system. The x and y and z components of the center of mass are calculated in the same way, but utilizing the part of the location which is relevant. For example, the horizontal displacement of the segment is used for the x component at the center of mass, assuming that the x-axis is the horizontal axis. The center of mass itself may have velocity and/or acceleration, which is computed in the same fashion as the x and y components of the center of mass, but utilizing the acceleration or velocity vector components of each segment. High diving is an example application because it involves body alterations to optimize rotation, twisting, or both. Diving is done off either springboards or platforms, with the lowest being 1 meter and the highest 27 meters. Different body shapes shift the center of mass and the radial distance of the body system. The rotational momentum and speed changes with these body positions. For example, one may arch slightly for a twisting rotation to forcefully create an upward motion, which generates a rolling motion. To maximize flips, divers pull into a very tight tuck position where you grab onto your shins and pull your head between your legs, squatting down. Finally, for slower rotating, gaining torque for twisting, or stopping tuck rotation, divers enter a pike position where you completely fold in half. Here are steps on why the center of mass is important for springboard launch. If your center of mass is not over the board but instead leans forward, like this, the diver does not get enough height to successfully complete the dive. However, if you lean backwards, back there, your knees will buckle and cause you to fall. Center of mass has applications throughout the dive. Furthermore, divers also utilize center of mass shifts to minimize splash. This video demonstrates this effect. What happens when you don't pull into a tight enough center of mass, or when your center of mass drops forward instead of remaining balanced on the end of the board? This video demonstrates the importance of the center of mass. Notice how the diver dropped forward before launching into the reverse dive, or how the diver opened up after the first somersault as opposed to staying in a tighter tuck. Both are components which impacted the painful landing. Here is an example problem. Suppose a 75-kilogram diver is 170 centimeters tall, with 30 kilograms concentrated in their torso, 70 centimeters long, and the rest evenly distributed over their body, when outstretched. Suppose their arms and legs are the same length. Where is the center of mass when they are in a pike position? Where is it when they are in a tuck position? First, it is important to note that because the mass is evenly distributed over the length of each leg, arm, and torso, we can calculate the point mass by finding the middle. On the left, we have a phobeta of the person 170 centimeters tall. Here we have the arms and legs calculated. Then we have the pike position and how we are treating the stacked point mass ligaments, labeled A and B. Based on the geometry, mass A, which is the torso felled in half, has a length of 35 centimeters and a mass of 30 kilograms. Evenly distributed, so its point mass is at 35 centimeters divided by 2, which is 17.5 centimeters. Mass B, arms and legs, has a length of 50 centimeters and a mass of 45 kilograms total. Its center is at 25 centimeters, positioned after mass A, which is at 42.5 centimeters. The legs is going to have 25 for tuck. The center of mass calculation is performed below, resulting in a 32.5 centimeter horizontal center component, assuming the far left side of the block A is the zero value. On the right, we repeat these steps, but for the tuck position, demonstrated by the two blocks given. We end up with a 28.5 centimeter center of mass. Notice in this scenario, the center of mass is in the y direction, whereas in the previous, it was in the x direction. This is due to the way our fibula is positioned.